We're going to straight dive into a learning check for part 3 of buffers. Here it says, what is the pH of a buffer made by adding 40.0 ml of 1.0 molarity of potassium chromate to 10.0 ml of 1.5 molarity of NaOH? So let's draw an image of what's actually happening here. So we want to make a buffer solution. And to make us buffer solution, say we have a Erlenmeyer flask here, and we're going to add in 40 ml, 40.0 ml of potassium chromate, and that concentration is 1.0 molarity of HCrO4. Then we take another substance, which is NaOH, a very strong base, NaOH, and we're going to take 10 ml of that, 10.0 ml, and the concentration of this particular NaOH is 1.5 molarity. We're going to take these two substances and mix together in here. So in here, you're going to have your NaOH mixed together with plus KHCrO4. And there's going to be some kind of reaction. But notice something here that this doesn't really look at a buffer system. Why might not look like a buffer system? Well, that's because if you look at the NaOH and KHCO4, can they be a buffer system? Here you have a very strong base, whereas over here you have a weak acid. In fact, this can act as a weak acid and a weak base. It just sort of depends on how it's going to react with its counterpart, which is the strong base here. Since we're working with strong base, this most likely is going to act as a weak acid. But can they be a buffer system? Because they are not a conjugate of each other, you might think that how could this be a buffer system? If it was a buffer, I should have this acid and its conjugate base, which would have been, K2CrO4. And so we kind of have this question there that they are not conjugates of each other. So NaOH and the HCrO4 are not conjugate of each other. Conjugate of the CrO4 would be CrO4 I apologize, K2CrO4 or CrO4 2 minus. Also notice that this strong base is present. We have talked about how buffers must be a weak acid and a weak base counterpart existing together in a solution in order to be a buffer. But here you'll see that there's a strong base present. So you might question this particular learning check, the question in itself. However, even though this is not a buffer system to start with, the thing is when they react together, okay, they can potentially form a buffer system when they react together. So the strong base and the weak acid reacting together can become a buffered system. And I will more illustrate further and what's happening here in the next slide. So let me take all of this out so we can do some calculation. Okay, so let's move on. Let's write the chemical equations. So we're going to take out any of the spectator ions that are shown here so that our molecular equation will be much simpler. So let's take this right here, potassium chromate. What is the spectator ion here? Right, this is the K. So we're going to take out the K. So if we take out the K, we have HCrO4 minus. Since K is positive 1, so HCrO4 is minus 1. What's the spectator ion here? Hopefully you're able to say sodium, and sodium is the spectator ion, so therefore this is just OH minus. So we have our base here, and we have our weak acid here. So how will they form? Base is going to accept the proton or the hydrogen ion from the weak acid, so forming water liquid, and then this will become so a CrO4 and then 2 minus because H has been taken out. So these are all in rest are in aqueous form. Okay, now what we're going to set up is what's called the ICF table. Not ICE, but ICF. We've learned this before. And the ICF table, YF. Why not E? Why not the equilibrium? And that's because this has a very strong base, and anything you have something that's strong base or strong acid, it's going to go into completion. So there is no coming back or very little. So therefore the arrow is in one direction, and so this is the ICF table, which does not show equilibrium but rather final. Okay, let's talk about what goes in here. Well, what's going to go in here are millimoles. Millimole. And then millimoles. And all of these in here. How can we solve for millimoles? So let's find the millimoles for the hydroxide first. So hydroxide, I'm going to write off to the side, hydroxide. And hydroxide has a concentration of 1.5 molarity and a volume of 10 ml. So 10.0 ml, and you're going to multiply by the molarity, which is 1.5 moles over liter. And remember how we said we give you a little trick. You can just cancel out the L's. And so we get 10.0 milli, right, times 1.5. And that, if you punch this into the calculator, it's 15 point, that's 15 point with the right sig figs, and then that would be millimoles. Okay, so I have my initial as 15 millimoles here. Then we have our HCrO4, okay? How about that one? Well, there are 40.0 ml, and there's 1.0 moles over a liter. And the liters cancel out. And so if you calculate this out, 40.0 times 1.0, that would give you 40 millimoles. So that's going to give me 40 millimoles. All right, and then we haven't made any of the carbonate. And since water is a liquid, we don't count that, okay? If it's a liquid, only the aqueous, folks. Okay, and there's going to be some kind of change. And what is this change going to be? Well, the change is going to be the limiting reactant. Because this is going to completion, you're going to look at the one with the lowest value of the reactant, and the lowest value of the reactant is hydroxide. And it's nice because it's 1:1:1 ratio, so we're going to look at 15 millimoles, and you're going to subtract 15 millimoles for all of the reactant present. But on the product side, it's going to add 15 millimoles, so plus 15 millimoles. In the final, you're going to add the top, the I, and the C together to get the final. So 15 plus negative 15 would be 0. 14 plus negative 15, that's 25. Lost my train of thought for a sec. And then 0 plus the 15 is 15. So here I have the millimoles. After you find the millimoles, you want to go into the concentration. So you want to find molarity. To find molarity, you must have moles and you must have liter. Well, how much liter? We will have to add the total amount of volume. So total volume is equal to 40 from the HCrO4 and also the 10 ml from the hydroxide, so plus the 10.0, and so that would give me 50.0 ml. Now I can take that particular milliliters and divide it by 50.0 milliliters for both of the concentration. We're trying to find the concentration. And then we're going to cancel out the M's, right? Cancel out the M and find out the molarity. So the molarity, if you were to punch this in, 25 over 50 would be 0.5. And keep it at the correct sig phase, 0.50 molarity. And for here, for its conjugate base, 15 divided by 50, if you were to punch this out into the calculator, you would get 0.30 molarity of CrO4 2 minus, and this is HCrO4 minus. So let me just kind of take you back and come back here. Remember what I have mentioned in the previous slide. Can this be a buffer system because it has a strong base and a weak acid? And initially, by looking at just these two compounds, it's a no because one, they're not conjugate of each other, and also strong base is present. However, when they react together, right? When you react together, you will notice the strong base has been depleted. There's no more, and you will find that the weak acid, there is now a weak base, the conjugate. So let's go back. Look at this. All of the base has been diminished, right? It's at 0 now. The weak acid is present, so is its conjugate base over here, and they're both present. Having this both in presence lets me know that this is or can be a buffer system. Now, I haven't answered the question yet, which is what is the pH of this particular buffer system? So let's go ahead and write the equation of the Henderson-Hasselbalch equation, which is pH is equal to pH is equal to pKa plus log of the conjugate base over the acid. Well, what is pKa here? Well, the Ka is given already, and it's K2, not K1. And the reason is because this CrO4 could be H2CrO4, and this is the second value. If you look in your reference sheet, you'll notice that the KHCrO4 is actually falls under K2. Ka2, and so therefore I have the Ka2 already written out here for you. All right, pKa means negative log of K2, which is 3.20 times 10 to the negative 7. Log of the base, which is my chromate here, CrO4 2 minus 30, all over 0.50. Okay, and then we're going to go ahead and calculate this out and get the pH. The negative log of 3.2 times 10 to the negative 7, and then I'm going to press enter. All right, there's that long number there, plus then I have my log of 0.3 divided by the 0.5, right? And then I'm going to press enter. And that gives me 6.273 and this big old number. And then with the correct sig phase, it will be 6.3. So my pH value is 6.3.